When we compile a high-level language into an executable, it often looks like a seamless process going from the high-level language to the executable binary. What in actuality happens is a series of steps. First, the high-level language is compiled into an assembly source file. Second, the assembly is turned into an object file binary, which is the machine code, but is not yet in executable form. And then we use the linker to turn that object file into an executable. In this lecture, we will step through each of these processes one at a time. To do this, we will work through a very simple piece of code. All it does is declare a few variables and then print to the command line and then return control of the processor back over to the operating system. Let's look first at the process of compiling to assembly. On the left, you'll see the GCC command to compile an example program test.c into an assembly language piece of code test.s. On the right, you will see code generated by the GCC compiler for our example program, and this is done in x86 assembly. Some things that you should be able to notice. First, here's our main function. We have a main label, and then we also allocate some stack frame for our main function. Next, we have our variable declaration of a. We are storing the value of 0 for that variable a. Then we add 5 to a to store it into b. Then we prepare everything for our printf function. We call the printf function. And then we deallocate our stack frame, calculate our return value, and return control to the operating system. Now, something you might notice about the printf function is that nowhere in this assembly code is it actually written how to execute the printf function. There's no label for printf. And so what's really important here is this piece of code down here, which is called the relocation information, which tells us that we need to look elsewhere for the printf function, and the linker will use this information later to connect us to that printf function. One reason we like to write in high-level languages and use compilers is that, one, it's easier to program, but two, compilers generally do a good job of writing code that is transportable across architectures and implementations of an ISA. Now, after we've compiled, we will assemble the assembly code into an object file. At the top of the screen, you see the instruction on GCC to create an object file. And down below, you will see part of an object file that was created from our test.c program. The object file is pretty much unreadable because it's written primarily in binary that is meant to be machine code and is meant to be interpreted by the architecture and not humans. And so you'll notice there's a bunch of gobbledygook that we don't really understand, and that's totally okay. But I do want to point out a few things about how the object file is formatted. So first, we have the object file header, so you can see at the arrow, there's a myprogram.c, so there's some header information that explains what we have. You can also see a little bit to the right the main function label telling us that this is where our program will start. After that, you'll see the text segment, so this is where we're saying this is where our code is going to be and how we're going to allocate that text segment. Then we'll have our data segment, which explains where to put global data and stuff like that. And then finally, down at the bottom, there's our relocation information and our symbol table, which again the linker will use to figure out that it needs to find the printf function somewhere else and fill that information in that's missing currently in our test.c. So once we've compiled and assembled it, we're ready to link our code to other object files. At the top again, you will see the GCC compiler instruction to go all the way to an executable. And what's hidden in here is that the linker is the last step. While our program here in test.c is not really that complicated, it is very likely when you start writing large programs with millions or hundreds of thousands of lines of code that you don't want to have to compile every single time, every single piece of code that you have. And so what we can do is compile different source files separately and stop at the object file and only recompile the files that we need at a given moment. The object files can be recombined as needed by the linker when we want to be able to recompile pieces of code that use multiple different source files and multiple different object files. And notably, the linker also connects our object files to program libraries such as standard I/O. The linker finds all the data that's missing and turns it into an executable file that can then be run on our computers. So how does a linker do that? So first, basically what you're going to have is you're going to have multiple object files. Let's suppose, for example, in this case we have a object file that has a main function, and it calls a subtraction function, which is in a different object file, and it also calls the printf function, which is in a standard C library. What the linker will do is it'll look in the location records for symbols such as sub and printf, and then it's going to look in the other object files to find those same symbols sub and printf. The linker's job is then to figure out how to combine all of these to basically create pointers that will let us to call sub from the other object file, create a pointer for printf that we can call from our main function as well, and then it'll put those pointers into our executable at the end. It will also put the printf function and the subtraction function into our executable so that they're all available in one location for the architecture. Finally, once we have our executable, the OS is going to run a program called the loader to begin execution. So it goes through a series of steps to do that as well. First, it's going to allocate some memory in the main memory for our program, based on how much space it needs for our text segment and our data segments. And then it's going to copy the text and data segments into their respective places in the memory image. Then, after it's got the text and data segments available, it's also going to copy the program arguments that come from command line instructions onto the stack. So those -s or the -c that we showed you earlier from the compiling commands would be arguments that would be copied onto the stack so that the program can call those arguments from the stack when needed. Then the operating system will clear the registers and set the stack pointer to the correct location so that we can find those arguments that we just copied onto the stack. Then it copies those arguments off the stack, puts them in the appropriate registers for us to use, and then jumps to the main function.